We're recording. Okay, so are there any questions on the homework that's due tonight? Okay.
I had a quick question.
Go ahead.
So it was under 5 point, I guess it's 5.1 under the add and subtract polynomials. And I had just had like a not a specific question from the homework, but just the function of like when you have the function of two different polynomials or two polynomials, and then you have to so the one you gave in the lecture was f minus g with a -2. And my question was more, do we have to plug in the number in the function and then solve, or can we sort of reduce the polynomial and then plug in after we've reduced the terms?
The answer is both are correct. Either one works.
Okay.
But yeah, you're talking like something like this where you're given two functions. Let's say what's one where some like letter B here, where you're given the two functions. Yeah, so you could either do, you could do first, you could talk about doing, f minus g of x, which would be the first equation. So x squared minus 9x plus 18 minus x minus 3. Work that out and then plug in x equals -1. Or you could plug x equals -1 into those expressions first, get the values, and then subtract those. The order itself doesn't matter.
Okay.
Since people tend to have, the reason why I did it plugging in first is then it's all numbers and people just tend to just visualize numbers easier than they do variables. But if you like doing this, if you like subtracting the variables first, then by all means, feel free.
Yeah, I find myself making more sort of simple mistakes by putting the number first and versus reducing it down.
Yeah, so either one of those is fine. And you can double check. You'll get the same answer either way. But yeah, that's
Okay.
either one of those is an acceptable solution.
Okay, thank you.
Okay. Any other questions on the homework? Or just questions for me in general? All right, so just as a note, 5.1 to 5.4 is due tonight. And that is what is going to be on quiz number 3, which will be due Thursday by 11:59 p.m. So tomorrow by midnight. Okay, so that will be the quiz that is covered, or the quiz material, I should say. It's basically chapter 5 stuff. All right. Oops, how do I always end up doing that? Okay. So not seeing any other questions, we will move straight into what I kind of want to do is I kind of want to do a factor roundup, which is we're going to finish up chapter 6 today, which is why we do all this factoring. We can actually use it to solve equations. But just to kind of reiterate, in general, when it comes to, the factoring kind of guide, if you will. And once again, this is probably literally the last thing you have in your notes. So you don't need to rewrite this down if you don't want to. But it's just so I have something I can kind of reference as we move through class today. Which is first step is factor out any common factor. Factor out any GCF. And then it breaks down to whether or not you have 2 terms, 3 terms, or 4 terms. So two terms, we had three cases, which was the difference of squares, the difference of cubes, and the sum of cubes. Difference of squares is a minus b, a plus b. Difference of cubes, a minus b, a squared plus ab plus b squared. And a cubed plus b cubed is a plus b, a squared plus ab plus b squared. So those are your two-term factors. Your three-term factorings, if you have that perfect square, a squared plus 2ab plus b squared, that factors into a plus b squared. And if you don't have that, then we'll have to go to a diamond. And anytime you have four terms, oops, we do factor by grouping. Okay, so like I said, I'm just really kind of rewriting this down. So we have this as a reference going into, we're going to be doing a bunch of factoring today. So kind of having this in a nice place we can kind of scroll up to will be handy. Or you can refer to the one hopefully you wrote in your notes from last class. Alrighty. Great. Okay, so that's going to move us into, so this is technically what 6.4 is. It's just more examples of this. We're actually going to skip 6.4 because it's just kind of a factoring roundup like I have right here. So we're going to move straight into applying this stuff in section 6.5. Solving equations with factors. Okay, so what we're going to do is we've done a bunch of algebra where we have stuff like this. If we have a single variable here, we can solve for this 3x plus 1 equals 10. We can do our little work here where we're going to subtract 1. So we get 3x is equal to 9, and then we divide the 3 out. So we're left with x equals 3. Easy peasy. We've done this probably 1,000 times in class. Maybe not 1,000, but close to it. The question is, what happens when we have a slight change? Where we have some non-like terms. We have the same variable, which is x, but not like terms. The problem here is that we can't get x by itself, because if I subtract over, well, the x and the 10 aren't going to combine. And also, if we try to do a thing where like maybe we divide by x, problem is now, I mean, the first one and the second one, we get, oh yeah, 3x plus 1. But now on the right-hand side, I have 10 divided by x. So I've moved the variables around, but it doesn't really make it an easier problem to solve. So we need a new technique. And the answer is going to be factoring mixed with one other property. And that is going to be what we call the zero product property. And it's a very, very simple idea, which is that if a times b equals 0, then the only way that you get a product of 0 is 1 or both of your numbers are 0. One or the other has to be 0. So if we can get this into a multiplication, we can then proceed to break it up into the two terms, which is a equals 0 and b equals 0. We can separate it out as single variable equations. So if we're asked to kind of solve this, once again, pulling this guy out, if we have a slightly different equation, Let's say that equals 0. Well, once again, going back to my factoring, the first step is to see if we can factor out any GCF. And in this case, we could. We could factor out an x. So that would leave me with 3x plus 1 equals 0. So what we've done is we've created this product. Technically here, x is holding the place of kind of like my A, where 3x plus 1 is kind of holding the place of my B. So then what we can do is separate this out into two equations. Actually, I'm going to slide this up just a little bit so I have some more room to finish this problem. Which is the first one, which is the A part, x equals 0. And the second, the B part, which is 3x plus 1 equals 0. Well, this first part's already solved. X equals 0. That's one of my solutions. And then here we have to do a little math. Subtract over the 1. And then divide 3. So we get x is equal to -1/3. That's my second solution here. So for a lot of these polynomial equations, we are going to have more than one solution. So this one has two solutions, 0 and -1/3. Okay. Questions on this? All right, so the goal is to always, once we have one side equaling 0, and that's the important thing, it has to equal 0. We'll get into why in just a second. I mean, it's right here because we know one of them has to equal 0. But once we have a set equal to 0, we factor, and once it's factored, we're going to break it up into two separate equations that equal 0. Okay. Why does it have to equal 0? So same idea, which is, let's say he's like, all right, let's just do what we did last time, which is let's say factor out. We factor out an x, and we have 2x plus 3 equals 2. The reason why 0 is the magic number is that if it equals 0, one of the numbers has to be 0. Here, one of the numbers doesn't have to be 2. It could be the case that x equals 2 or 2x plus 3 equals 2. It could also be the case that x equals -1 and 2x plus 3 equals -2, or x equals 1 and 2x plus 3 equals +2. Or we get stuff like x equals 1/2, 2x plus 3 equals 4. The problem is if it's not 0, there are all these combination of numbers that could multiply to give us 2. Why 0 is special is if you multiply to 0, one of them has to be 0. There's no way around that. So usually what our first step is going to be then is if it's not equal to 0, we're going to 0 it out. And you can go either side. Obviously, we could either subtract these two pieces over to the right, but I think it's a little bit easier to just subtract the 2 over. So we have 2x squared plus 3x minus 2 equals 0. So we've zeroed out one side. Let's actually write this in bold so people look into the notes later. Okay. So we're here. Now we've got a trinomial. So we're going to go through and factor Remember that we've got A, B, and C. So we have A times C up top, B on the bottom. So we've got -4 and 3. And the goal, once again, with these diamonds is we want to multiply to the top number, but add to a bottom number. So 4 is pretty easy. The only numbers that multiply to 4 are 2 and 2, and 4 and 1. 4 and 1 is how we're going to get that value of 3. We know one of these has to be negative. Since the bottom is positive, that means that the bigger number is positive and the smaller number is negative. All right, so now we're going to do is these numbers right here. Actually, I like to color code these. +4, -1. That is going to tell us how to break up our middle term. So it's going to be 2x squared plus 4x minus 1x, or just minus x, and then minus 2. Technically, we're equaling 0. Honestly, you can kind of drop the 0 until we get it factored out. But if you want, in the most technical sense, we need, as we work down the side, the right side always equals 0. Working out the factor by grouping. Both of these have an x attached, so we have an x and a 2 that we're going to factor out. So that'll leave me with x plus 2. Here, both of these are minus, and notice that we've got x minus 2 and x plus 2. So if we factor out a -1, I get the exact same expression, which is what we always need in order to do this factoring, which is we need that same, binomial. So if we work this out, we have x plus 2 times 2x minus 1 equals 0. So we've now factored this out. And so our last step is we're just going to separate this out and solve. So the two pieces are going to be x plus 2 equals 0 and 2x minus 1 equals 0. First equation, we'll just subtract over the 2 and get x equals -2. On the right-hand side, we'll add the 1 over and divide the 2, and we'll get our second value of x equals +1/2. Okay. Question on this example, anybody? So for the most part, this is really 90% of the work we were doing on Monday is just factoring, which is what we were doing last class, right? It's really mostly factoring, and then at the end, we just tack on this light little step where we do some very, very simple algebra, where we split it up, and these, once we have it factored, these are usually very, very quick solves. So it's really just factoring with just this one extra step where we set it equal to 0 and solve our equation. Okay. Questions about this, anyone? All right. So same thing, same prompt we're going to solve here. Now, once again, be on the lookout for our shortcuts. We have 3 terms, and if we go back here, we have a case where the first and the last term are perfect squares. So remember, our trick here is we kind of just double check. This is a perfect square of 9x. Here we have a perfect square of 5. If I multiply those 2 things together, that gives me 45x. And here we're exactly double. So because of that, we can go straight to, this is going to factor into 9x plus 5 squared. And once again, you could go back to doing the diamond. It's just, it's kind of a messy diamond. You could go through and do the diamond on this where you take, your A, your B, and your C. It's just, it's kind of a messy diamond because the numbers are so big. Technically, it's 45 and 45 are the numbers that work out, but that can be kind of hard to see. Okay, so we factored it. The next step is, remember what it means to be squared is that this is 9x plus 5 times itself. So if we split this up, actually I'm going to do this. We slide this up. No, screw it, let's finish this out. We kind of get the same equation twice, right? 9x plus 5 equals 0. 9x plus 5 equals 0. Obviously, we don't need to solve it twice. We can just solve it once and be done. So if we subtract over the 5, we get 9x equals negative 5. And if we divide by 9, we get x equals to negative 5/9. So sometimes there is only one solution. Here is a case where that happened. There's only one solution of x because when we factored down, we got the same binomial factor twice. So it repeated. Alrighty. Any questions on this example?
I got a question.
Go ahead.
You don't simplify at the end, you just leave it.
What do you mean simplify it?
Like when it's like when you mention 5/9, you just leave it. You don't simplify because it's not. It doesn't go into each other. You just leave it.
Well, there's no. If we could simplify the fraction, I would, but there's no way to simplify that down. That's in its lowest reduced form.
Oh, okay.
If we'd got negative 10 over, I don't know, 18, then we would have simplified down, factor out a 2 to get that negative 5/9. But in this case, negative 5/9 is simplified. There's nothing, we can't bring down those values any lower.
Oh, okay.
Okay.
Yeah.
All right. Next one. All right, 3x squared is equal to 108. So once again, if that right side doesn't equal 0, I'm going to make it 0. So my first step here is I'm going to subtract over that 108. So if we go back to our little factoring tree, factoring chart, I should say, we see that we've got 2 terms. And we've got squares, but we don't have perfect squares. So how do we go about this? Well, remember that the first step is always to factor out any common factor. And well, we know 3 goes in here, and as it turns out, 3 will divide evenly into both. Now, honestly, you can either keep that 3 or leave that 3. It really doesn't matter. Let's talk about why. So here we have that difference of squareds formula. So here, there's a perfect square of x, this is a perfect square of 6. So this would factor down into x minus 6, x plus 6, with that 3 in front. So we've got a product of 3 things. So if we set them equal to 0, technically we would have 3 equals 0, x minus 6 equals 0, and x plus 6 equals 0. So 3 doesn't equal 0, so it doesn't even, we don't need to worry about that giving us any solution. Here, if we add over, we get x equal to positive 6. Here, if we subtract over, we get x equals negative 6. So another reason why the 3 doesn't really matter is if you want, right here, what you could do is if you have 3 times x minus 36, oops, x squared minus 36, I should say. What you could do is just divide both sides by 3 and just get x squared minus 36 equals 0, which is going to have that exact same factoring, which ends up giving you, oops, those same values. Alrighty. Question on this, anybody? All right, let's look at one that's a little more, just a little more involved. Technically prompt for all these. All we're doing here is solving. It's just we solve by factoring. All right. So once again, we're going to zero out one side, and you can go either way. You can take the 6x and move over here. Personal preference, I like to have my highest power be positive because it makes the factoring a little bit easier. So in this case, I'm going to actually decide, even though it's more terms, I like my highest power term to be positive, so I'm going to move these two pieces over. So I'm going to have 0 is equal to x cubed minus x squared minus 6x. Once again, when factoring, we always want to see if there's anything common, and we notice all of them have got an x attached to them. So if we go by the lowest power, that would be an x to the first, or just an x that we factor out. So that would leave me with x squared minus x minus 6. All right, so working this out. So now we have the second part that we need to factor. So once again, looking at this, we've got minus 6 and minus 1. So things that multiply to 6 are 3 and 2. Those can be 1 apart with a negative. Since the bottom is negative, that means my bigger number is negative. And remember, in this case, we had that shortcut, which is if there's a 1 in front of your x squared, then whatever the numbers are on your diamond, those are going to be the numbers of your factor. So in this particular case, and once again, that case is when we have a 1 in front, those numbers here correspond exactly to those numbers on the factor. All right, so now once again, we're going to have to split this up, and this time we actually have a variable on that outside piece. So we're actually going to have 3 answers here. We're going to set up the first one as x equals 0. x minus 3 equals 0, and x plus 2 equals 0. So this one's already solved. That one's done. My first answer is 0. If we add over, we get x equals positive 3. And if we subtract over, we get x equals negative 2. So in this particular case, this equation had 3 solutions that work. Great. Questions on that, anybody? All right, so this last one's kind of a trick question. It can kind of throw students off. Unless they see it for the first time. Which is, this kind of looks like it's at the end of one of our problems. Like, oh, it's factored. So we can go x plus 6 equals 9, x minus 2 equals 9. Once again, the issue is that the only time we can do this split up is if the right-hand side equals 0, and that's not the case. The right-hand side equals 9, so I don't know if it's like 9, or it could be x plus 6 could be 3 and 3. Could be, x plus 11, oh, sorry, pardon me. X plus 6 equals 9. X plus 6 equals 1. So there's just all these combinations of things that it could be if we keep it as a 9. And we'd have to check and see which ones work and which ones don't. Whereas if we just set the thing equal to 0 and solve, those will always give me the exact solutions. So unfortunately, we're going to have to do a little work to undo this, which is we're actually going to have to subtract the 9 over. But now we don't have this nice factoring, so what's going to end up happening is we're going to need to FOIL this piece out first and combine our like terms. So x times x gives us x squared minus 2x plus 6x minus 12. And then we have minus 9 equals 0. So once we combine our like terms, negative 2x and 6x gives us plus 4x. Negative 12 minus 9 gives us negative 21. And now we're back to a 3 term. We don't have perfect squares, so that means we're going to a diamond. So up top, negative 21. On bottom 4. The numbers multiplied by 21 are 7 and 3. And since the 4 is a positive number, that means that my bigger number is positive, which makes 3 negative. All right, so now what we have is our middle term. Actually, I stand corrected. Never mind. We have a 1 in front of the x squared. We don't need to do the factor by grouping because we have a 1 in front of the x squared. My factors are going to be just these numbers. X plus 7, x minus 3 equals 0. So now we can go to breaking up and separating out. So we get x equals negative 7 and x equals positive 3. Okay, questions on that anyway? Okay, so. All right. So that's the end of chapter 6, which is, we do first 4 chapters are all kind of getting into, or sorry, the first 4 sections, I should say, are all getting into factoring, how we set it up, the techniques for it, and that culminates in chapter 5, which is we use this to solve equations. And for a lot of the stuff we do for the back half of this course, 6 all the way up through 12, is that we're going to do a lot of work. Like the first couple sections are going to be setting up how do we do a specific technique, what are the rules of it, when can it be applied, and eventually the goal here at the end is to lead into, well, we're going to use that to solve equations that contain those things. So here we learned how to factor because it really helps us solve a new type of algebra equation. Okay, any questions on anything I've done so far? All right. Next chapter. Rational expressions. All right, so we've already done a little bit in terms of rational expressions, kind of. So let me get in this real quick. Rational expressions, you see ratio, you think fraction. So that's what we're looking at here. We're looking at just exponents, expressions, which are fractions that just happen to have a variable in the denominator. Something like, 45x over 60x squared, that would have some variables in the denominator. 1 over x plus 5. So these are technically rational expressions. We have a variable in the denominator. Sometimes we can simplify these, right? 45, we can pull a 5. Actually, we can pull a 15 out of both of those. And that would leave me with 3. And the x's, 3 in the denominator. And here the x's cancel. We're just left with 1 over 3x. And we've done work like this before, simplifying using a monomial. A couple questions will just have you working, let's say, with a function. F of x is equal to 1 over x plus 5. And we're just has to value like, oh, what is, f of 0? What is f of -5? So we're just plugging in, right? Just dealing with rational functions. So it'd be 1 over 0 plus 5. Well, that's 1/5. Or we could have -5, so we'd get 1 over -5 plus 5. And here we run into an issue. That's 1 over 0, that's undefined. So the thing that we run into with rational expressions is there are values of x that if I plug in, I'll get an undefined value because we're ending up dividing by 0. So what these are called is, this is what's called a domain restriction. So remember what domain means. Domain is the set of inputs. And what we just saw here is given f of x is equal to 1 over x plus 5. X equals 5 gave me an undefined value. So we can kind of say that in terms of what we can say is that the domain, or the domain restriction, is that x cannot be 5. All right. So You'll have a couple more questions where you're asked to find where where do we have an undefined value or where do we have a domain restriction? So let's do a couple more of these. Given g of x is equal to 3x plus 5 all over 4x minus 1. And you're asked to find any value where f of x is undefined. So, kind of like what happened in the last problem, when do we get undefined? We get undefined when we divide by 0. So what I'm looking for here is any place where my denominator equals 0. So we're just going to do a quick little solving here. Add over the 1 and then divide the 4. And our domain restriction or our undefined value for x is that x cannot be 1/4. Because that gives me 0 in the denominator, which is bad. Okay, questions on this, anybody? Now, note, the numerator does not play any part of this because the numerator we're just plugging in. The undefined value happens by dividing, so the domain restriction is always going to be caused by the denominator. We're worried about where that equals 0. All right, let's look at one more of these. Given h of x is equal to 5x minus 3 over x squared plus 5x plus 6. Find any values where g of x is h of x, h of x is undefined. Okay, so working this out. We're setting our denominator equal to 0, because that's where we find these values by setting our denominator equal to 0. And, well, this is basically just doing the exact same work we did in the last section. I'm solving this polynomial equal to 0. So the way I'm going to solve this is factor it out. So if we work that out, we have, technically that's a 1 in front, so 1 times 6 up top, 5 up bottom. So my numbers here are 3 and 2. And once again, since we have a 1 in front of the x squared, we can jump straight to the factoring as x plus 3, x plus 2. Once again, that trick only works when we have a 1 in front. If we had something different, we would have to do the full factor by grouping. But let's use our shortcuts when we got it. All right, so now that we have two equations, we're just going to separate them. X plus 3 equals 0, x plus 2 equals 0. So we get x equals -3 and -2. And these are my undefined values. Undefined values of x equals -3 and -2. Meaning if I plug those numbers in, I get an undefined value in my function because we end up dividing by 0. Okay. Questions on the function notation in terms of domain restrictions of these rational functions? Okay. So once again, the first thing we're going to run through a lot of this chapter is just running through things we normally do with fractions and just applying them to having variables in there. And the first thing you really learn how to do with fractions is you learn how to simplify, right? 3/6, you simplify down to just be 1/2. Now, what you've done so much in your head that you're just used to doing it is what's actually going on here is, well, this is 3/6 factors into 3 times 2. And what we can do here is cancel these out. And we're left with just 1/2. Turns out that when it comes to variable rational expressions, same truth holds. Once you have things being multiplied, if you have the same term up top and on bottom, you can just cancel out. So we can simplify something like, obviously we're going to start off easy. Here, what we have common is this x plus 2, an entire binomial is common. So once we factor that out, we're just left with the remnants of x plus 5 all over x minus 3. Sometimes these require a little bit of factoring. Up top, what we can do is factor out a 2, which will leave me with x plus 4. And then in the denominator, we have a difference of squares. So that factors into x plus 4, x minus 4 in the denominator. So once again, canceling out our like binomial, the only two things we're left with is 2 all over x minus 4. Questions on that, say anybody? All right, let's look at another one. Okay, so here we're gonna have to do a little bit of factoring on both ends, right? Up top, let's see, we got 9 and 6. My answer here is 3 and 3. Remembering that 1 in front, we can factor this into x plus 3, x plus 3. And then on the bottom, we've got negative 18 and negative 3, so that's 6 and 3, where the bigger one is negative. So that's going to give me, once again, because we have a 1 in front, x minus 6, x plus 3. So we factor, now we're looking to see if there's anything common. So we are left with x plus 3, oops, still in red. We are left with x plus 3 all over x minus 6. Why did I multiply the 1 by x squared is what someone in chat asked me. I'm not sure what you mean. I didn't multiply anything through by x squared. Are you talking about in problem A? Let's call this problem A, B, or C. Which question were you talking about? Oh, I didn't multiply the one. The one's technically always there. Remember that what happens is if we have a 1 in front of that x squared, so if we have 1x squared plus whatever. If there's a 1 in front of the x squared, then the numbers on the diamond are exactly the numbers on my factoring. If we have any other number than that, then we don't have those values anymore. So we have to actually go through and do the full factor by grouping. So I didn't multiply the 1. I recognize that there is a 1. Anytime you've got, x plus 4, if there's no number written in front, we can always assume that there's a 1 in front of that. Does that make sense, Carl? Great. Let's do one more of these kind of simplifications. Thanks, sir. So here we're gonna have an example where we're actually gonna have to do kind of some work off to the side where we do full-blown factor by grouping and everything. Okay, so I'm gonna do this first one in blue. So first we're gonna have the diamonds. Up top, remember we've got A, B, C, so 2 times -9 gives me -18. And on bottom we have 3. That's going to be 6 and 3. And since the bottom is positive, my bigger number is positive, which tells me my smaller number is negative. So in this case, we don't have a 1 in front of the x squared. So we are going to have to do the full factor by grouping. So 2x squared plus 6x minus 3x minus 9. So we'll factor by grouping here. Here we can pull out a 2x, which would leave me with x plus 3. And here we could pull out a -3, which will leave me with also x plus 3. So this is going to factor into x plus 3, 2x minus 3. So there's my numerator. Working the denominator. So again, we've got an A, a B, and a C. So up top, we're going to have 2 into 3 gives me a positive 6. On bottom, we have a -5. So let's see, it could either be 6 and 1, but let's see, does that work? No, because we would need some sort of negative here, and we need both of them negative. So it turns out this one we're going to use 3 and 2, where they both happen to be negative. And once again, since we don't have a 1 in front of the x squared, we are going to have to do the full factor by grouping. So just like before, we're going to have 2x squared minus 3x minus 2x plus 3. Separate these out. All right, so just like before, factor by grouping. Here we can factor out an x and be left with 2x minus 3. Here we can't pull anything out, but if we notice we've got a minus 2x and a positive 2x, a positive 3 and a negative 3. So the signs are almost the same, except they're flipped. So that just means we need to factor out a negative 1. And then we'd be left with 2x minus 3. So working this out, we have 2x minus 3, x minus 1. And hard part's done. Really, most of these problems are just an exercise in factoring. The new step we've kind of added is once you factor, well, if you've got two things that are the same, we're just going to cancel them out. So that's going to leave me with the final answer of x plus 3 over x minus 1. All right. Questions on this? All right. So one more kind of simplification trick that'll help you kind of work these out. Because technically, I mean, like I said, all we're doing here is we're just taking fractions and simplifying them down, right? 15 over 20, 3/4. The simplification requires a lot more work because in order to break it down, we need to factor these down, and that does take some work. But really, all we're doing here is just simplifying fractions, taking an expression, canceling out common terms to get a less complicated form. So in that vein, there's one trick that can happen, which is if you have something, so if we talk about if I have x plus y over y plus x, well, we can cancel that out, right? If these were terms, because x plus y over y plus x, the order of addition doesn't really matter. That's the same as x plus y over x plus y, which is just positive 1. Anything divided by itself is positive 1. That's easy. The one that causes some issues is what happens if we have a minus symbol. So let's kind of do an example. What happens here? Let's do a couple examples of, let's talk about, we'll just do two different numbers. 6 minus 5 over 5 minus 6, 8 minus 4 over 4 minus 8, 12 minus 15 over 15 minus 12. And just kind of see what happens, right? What happens when you have the exact same term, but separated over division? So 6 minus 5 is 1. 5 minus 6 is negative 1. 1 divided by negative 1 is just negative 1. 8 minus 4 is 4. 4 minus 8 is negative 4. And 4 divided by negative 4 is negative 1. Looks like we're starting to see a pattern here, but let's just finish this up. 12 minus 5 gives us negative 3. 15 minus 12 gives us positive 3. And negative 3 divided by positive 3, once again, gives us negative 1. So in that same vein, we can kind of just assume that x minus y is the same of y minus x is going to be that exact same thing, -1. The reason for why that is we can rewrite this fraction as x minus y. If I factor out a -1, this just becomes a positive x and a negative y, and now we can cancel. And so we're always left with -1. So this here is kind of the trick, which is if you have x minus y over y minus x, you can cancel that out, but it costs you a negative symbol. If they're addition, you can just cancel them out right out of the start, and you just cancel out, left with 1 like you always do when you cancel. If they're flipped over subtraction, you can still cancel them, but it requires us just adding a negative symbol at the end. So let's do an example of this. Okay, so first things first, as always, we want to factor out. So here we have a 3 common to both terms. And if I factor that out, that leaves me with x minus 2. Here we have a 4 common to both terms. And if I factor that out, that's going to leave me with 2 minus x. So this is what we were talking about. We have the exact same expression, just flipped over subtraction. So you can cancel these out, but that means on your final answer, you're just going to throw that negative symbol down. And then we're just going to write what's left over. Okay. So here's an application of it's a simplification rule that really only crops up when we're dealing with these kind of subtraction of variables. It's an easy trick, but it is one that you kind of just need to remember, which is if you have two variables flipped over subtraction, they do cancel out, but they cost you a negative symbol on your final answer. Okay, any questions so far? Alrighty. Last part of this section. Multiplication and division. So normally when we multiply, if we have something like, 3/4 times 1/3, we can just multiply across. And then if we need to, we can kind of simplify down. 3/12, same as 1/4. However, what we could also do is instead of multiplying, so here we did the multiplication first, and then we did the simplification second. Whereas what you could also do is instead, 3 and 3, those are going to cancel out and leave me with factors of 1. So we do the simplification first, and then if we multiply across, we get 1/4. So we do the multiplication second. So when it comes to simplification, not only can you simplify, if we have 3/3 times 4, we can cancel that out. But we can also cancel out over a multiplication dot. They don't even necessarily have to be in the same fraction, so long as they're on opposite sides of the fraction bar, we can cancel them out. Okay, so how does this manifest with variables? All right. So once again, 90% of the work you're doing on these variable problems is just factoring everything out. So just going through this piece by piece. Here we can factor out a 5. We're left with a p minus 1. Can't factor p, so we're just going to leave that alone. Same thing, 3p squared, can't factor that down, we'll leave that alone. And then on the bottom, we can factor out a 10 and be left with p minus 1. So now what we're looking to do is anything that can cancel, top and bottom of the fraction bar, we can. So the easy one to see is, well, p minus 1 cancels out. The 5 and the 10 we can also cancel out. We can cancel out a 5 here, and pulling a 5 out of that's going to leave me with a 2 there. The other thing we cancel out is the p and the squared cancel out as well. So if we look at everything we have up top, all we have left in the numerator is a 3p. And in the denominator, all we have left is a 2. All right, questions on this? Anybody? Alrighty. Let's do one more multiplication problem. And we'll talk about division real quick, which is really the same work. All right, so let's say, once again, this really is just testing how well can you factor polynomials. Okay, so once again, just kind of color coding this. First one we have here, 3 terms means we're doing a quick little diamond. Oops, I apologize. That should have been a, excuse me. That needed to be a 2, or this doesn't factor. Let's double check this. X squared plus 2x minus 16. X squared minus 4x plus 3. X minus x squared. Yeah, sorry. X squared. That should be just plus, pardon, plus x minus 20. Yeah, sorry about that. Okay, so working this out, we got a little trinomial. So up top, we've got negative 15. On bottom, we have a 2. So 15 is 5 and 3. Bottom is positive, so that means the bigger number is positive, the smaller number is negative. And notice for all my expressions, we have a 1 in front of the x squared term. So that means we can go straight into the diamond gives us the factor of x plus 5, x minus 3. All right. Next one in red. Once again, we're just going to do a bunch of quick diamonds. We've got 3 and negative 4. Well, the only things that multiply to 3 are 1 and 3. And the only way to get a negative 4 out of that is to make both of those numbers negative. So once again, 1 in front of the x squared means we can jump straight to x minus 1, x minus 3. All right, up here. This isn't a diamond. We've only got two terms here. They aren't perfect squares. The only thing we can kind of do here is factor out a common term of x. And if I factor out that common term, that's going to leave me with 1 minus x. And then working out this last one. Once again, a quick little diamond. We've got negative 20 and 1. So it would be 4 and 5. Bottom number is positive, so the bigger number is positive. Smaller number is negative. And then we have my last factor, which is x minus 4 plus 5. All right, hard part's done now. We've done all the factoring. Now we're just crossing stuff off. So just kind of grabbing my red pen, just canceling some things here. We've got an x plus 5 and an x plus 5. X minus 3x minus 3. Actually, I'm going to slide this one up. So I've written it right. We also have, due to the subtraction, x minus 1, 1 minus x also cancel, but it costs us a negative symbol. So we'll just plot that negative symbol at the end. And that's it. What do we got left? X over x minus 4. All righty. Questions on this, anybody? All right. So multiplication, very simple. We factor and cross cancel. Division, remember that dividing fractions. Dividing fractions is very simple. We just multiply by the reciprocal. So that would give me 3 times 3 is 9 over 8. If there's any cancellation, we'll look for that. But if not, we'll just kind of deal with what's left. But in general, for division, we take the second fraction and flip it. And then we change the operation to multiplication. So if we have something like, oh, I don't know. Oops, wrong order. 3k minus 6. All over 4k squared. And once again, the prompt is literally just to divide and simplify. Alrighty, so division just says we take our second fraction, reciprocate it, and then we multiply by the reciprocal. And now we're going to go back to doing what we did before, which is we're going to go through and factor all these guys. So factoring that out, we can factor out an 8 out of that, which leaves me with 2 minus k. That's a k, by the way, 3k. We can't factor 3k, so that's left alone. 4k squared, can't factor that, so we'll leave that alone. And then lastly, we can pull a 3 out of that to give me k minus 2. All right, so looking what cancels. Once again, just grab my red pen and start crossing stuff off. The 2 minus k and the k minus 2 cancel, but they cost me a minus symbol. The k and the squared cancel. We can factor out one of those k's. And that's pretty much it. 8 and 3 and 4 and 3 don't cancel at all, so we're just going to multiply what's left over. Why does it have a negative? Because these terms right here are not exactly the same. They're flipped over a subtraction symbol. So the reason why it has a negative is that if it's flipped, we can still cancel them out, but the cost is that we have to add that negative symbol at the end. Because normally if you flip subtraction, you get the same value, but it's a negative value. Does that make sense? Great. So yeah, now we're just multiplying across. We've got an 8, a 4, and a k. So 8 times 4 is 32 times the k. And then on bottom, what do we got? 3 times 3. Boom. Done. That's it. So division works exactly like how we work in the rest of these, right? Because the first step with division is we flip it, becomes multiplication, and then it becomes exactly like the rest of these multiplication problems we did. So the division literally only stops you. It adds one little step, which is just flip that second fraction. Okay, question on this example, anybody? All right, so that finishes 7.1. We're going to get 7.2 in just a second. But before that, let's take a little 10-minute break. I got 5:50, so we'll be back at 6 o'clock even. So get up, stretch, grab some water. I'll be right back as well. Hey, everybody, welcome back. Let's see. We covered. Checking one thing in the assignment log real quick. Let me double check. Yeah, let's probably do it. I don't want to. We have a little bit of time. I do not want to. So I'm technically going to go past what's due next week. But I really just kind of want to get a little bit of a head start because the next couple of sections can be kind of meaty, and I don't want to rush through them because it's the more difficult content in this chapter. So I kind of want to take my time with it. Okay, 7.2. Adding and subtracting rational expressions. Okay, so once again, we're going back to fractions. How do we deal with fractions? How do we add them? So in general, if we have the same denominator, well, we can just do, oops, 2 over 12. If we have the same denominator, we can just add them together. 8 plus 2 gives me 10 over 12. Note that when we add, and this is different from multiplication division, when we add, we don't change the denominator. That stays the same. We just add the numerators. At the end, we might need to do a little bit of simplification. 10 over 12 becomes 5/6. So when we have variable expressions, if we have the same denominator, it's going to be the exact same thing. If we have 7/2x² plus 11/2x², the denominator is not going to change. And we'll just take the numerator. 7 plus 11 gives us 18. And if we can, we'll try and simplify down. 18/2 simplifies down to be 9/x². Another example, let's say we have something like this. m/m² minus p² plus p/m² minus p². Once again, doing any sort of addition or subtraction, the denominator stays the same. And these are not like terms, so we're just going to combine them like this. We're just going to say m plus p. Keeping what we just did in the last section in mind, though, there are times we can factor down. This is a difference of squares, right? This is a perfect square of m. This is a perfect square of p. So we could factor this into m minus p, m plus p. And here we can do a little bit of cancellation. And just be left with, well, we have nothing up top, so we're just going to write that as 1 all over m minus p. Okay, so like, and you will have a couple in the homework where you have like denominators. It's really just add the numerators across, simplify. The question is, well, what happens when we don't have like denominators? And let's kind of go back to what happens if we don't have like denominators with regular fractions. Because really everything we've been doing with variables, we've been modeling on what we always do with fractions. So the key thing we're always looking for is that least common denominator. And once again, there are a lot of common denominators that work, right? 24 is a multiple of, really we're looking for something that's a multiple of both. But what we're really looking for is the lowest common denominator. So in this case, if I have 4 and 6, my lowest common denominator is 12. So, let's actually write 12 here. What we do with the LCD is we want to take our fractions and multiply them in a way that gives me this common denominator. So on the first fraction, if we want to get a denominator of 12, we need to multiply by a 3/3, and it's always the same top and bottom. The reason why we do that is 3 divided by 3 is just 1. And if you multiply by 1, you don't change the value of an expression. And on the right-hand side, we're going to multiply by 2/2. So this becomes 3 times 3 is 9/12 plus 2/12. And now we've set up our common denominator. And now we have 11/12 like we need. Okay. So this is what we're going to try and build towards. If we don't have a common denominator, we're going to make one. And here's how we're kind of going to talk about making one. So we're just going to do a couple examples of what an LCD with a variable looks like. So first couple is we're just going to look at, given two fractions, what is the LCD? That's really all we're going to do for these first couple of problems. Let's recognize what the LCD is before we actually go through and do all this multiplication stuff. Okay, so we're still going to keep the same thing with the numbers, right? 5 and 2, LCD would be 10. And since these both have an x on there, we're going to need an LCD of 10x. Pretty straightforward stuff. If I have 1 over x cubed, if we have differing powers, and 1 over x to the fifth, and the same thing, we're asked to find an LCD. Let's write it like this, fractions, LCD. General rule of thumb for the LCD is you always want to pick the highest power. Because if I want something that's both a multiple of x cubed and x to the fifth, we always want the highest power. So in this case, I'll write that highest power. My LCD here would be x to the fifth. Okay, let's go over a couple more. Okay, so in terms of the variables is usually the easier part of the LCD, right? We've got x and x to the fourth. X to the fourth is going to be the variable part of the LCD. Now, once again, if you're decent with this, you can just kind of eyeball it. If not, when it comes to what is the number, what's that coefficient of the LCD? If you're ever trouble seeing it, once again, just pick the highest value and just keep going up multiples, right? So 8, well, 6 isn't going to 8. If we do another 8, 6 isn't going to 16. If we do another 8, 6 does go into 24. So 24 x to the fourth is my LCD. Okay, questions on any of this so far? Okay, so these look like pretty much how denominators look like we're dealing with normal numbers, right? We have this power with the variable, but honestly, that's not too difficult to see. What one of the difficult ones can be is when we have something like this. Which is, there are times when we've got two terms in a denominator, and this normally never happens when we're dealing with numbers. If we're dealing with numbers, we can normally just add this together and deal with a numerical expression. But if we're dealing with variables, there are times when we have not like terms, we have unlike terms, I should say, and we can't combine those to get one common expression. So the question is what the hell's the LCD in this case? This can be a little bit hard to see, so I'm going to actually plug in a specific number here. Let's let x equal 6. So that'd be 1 over 6 and 1 over 6 plus 1. So we're looking at the fractions of 1/6 and 1/7. So the LCD between 6 and 7, well, if you work that out, LCD here would be 42. And the only way to get 42 is you just take the first number times the second number. Since they have no common factors with each other, that means that there is no lower number than just their product. So what we'll just do is we'll take the two denominators, and this always works. You can always do this. It's just not necessarily nice. Like we could use x to the 8th, we multiply those together. X to the 8th would work as a common denominator, it's just not the least common denominator. But when it comes to these type of terms, if they have nothing in common, then the least common is their product. So when it comes to variable expressions like this, the LCD is going to be the product of just the two expressions. So if you just have monomials like this, then you're just taking the highest power and the lowest common multiple. If, however, one of those is a binomial, meaning there's an addition or a subtraction there, in that case, the LCD is always going to be the product of those two terms. Okay. Questions on that? Anybody? This is kind of the hard one to see because honestly, there's no direct comparison to a numerical part. This is something that really only happens when we're looking at these rational expressions that have variables there. You need variables in order to get these to kind of come out. Okay, so a lot of times, once again, we'll do one more expression that has a little bit more work to it, where we're going to find, once again, just the LCD. So let's say we have the following. 1 over x squared minus 2x minus 8 and 1 over x squared plus 3x plus 2. So we could just do the LCD as just those two things multiplied together, but what we usually want to do, a smarter way to do this is to factor these down a little bit. So once again, big deal, we do a lot of factoring in this chapter. What do we have here? -8 and -2. So that would be 4 and 2. Since my bottom is negative, that means this number here is negative. So this is going to factor into x minus 4, x plus 2. In red over here, we've got 2 and 3. The only numbers that multiply to 2 are 2 and 1. They do also happen to add up to 3. So here we have x plus 2, x plus 1. So here's why you factor this. This is a way to kind of shortcut and cut down on some of the work we need. Because what we notice here is that there's an x plus 2 on both of these terms. If I put in an x plus 2, I'm covering the x plus 2 here. I'm covering the x plus 2 here. Now here, they have nothing more in common. So then that just means we're going to attach on the x minus 4 and attach on the x plus 1. And there's my LCD for this kind of group expression. Once again, pause for any questions. All right, so now what we're going to do is we've talked about how to build the LCD. Let's actually use the LCD to add and subtract some of these variable expressions. So let's say we've got something like, let's start off easy. For all of these, the prompt is either going to be to add or subtract and simplify if necessary. Okay, so start off easy. So first step is always to figure out what my LCD is. Once again, we both have a common term of p, and 8 is already a multiple of 2. So that's my LCD. So what that means is I'm going to take, we want to get an 8p in that denominator, so I need to multiply this bottom by 4. And whatever we do to the bottom, we do to the top. On the right-hand side, we already have the 8p that we want, so we're not going to screw around with that. So we're just going to have 4 times 5 is 20 over 8p plus 3 over 8p. One thing to be careful about, do not simplify now. Because if you simplify, oh, well, you'll pull out the 4 and then you'll get back to here. We don't want to simplify until after we add down. Once you do all your multiplications and you get your, if you have common, I'm going to say this another way. If you have common denominators, don't simplify. Because if you simplify, that's going to get rid of your common denominators. So now that we're done, the denominator stays the same. And then we just add what's up top, 20 plus 3. That's 23. Easy peasy. All right. Questions on this, anybody? Do this, do. All right, so we're just going to run through a couple more examples. Once again, we're going to go through, pretty much what's going to happen is the denominator is just going to get a little more messy. Let's go y. All right, LCD time. So this is that case where we've got a binomial. We've got nothing in common here in terms of multiplication, because remember, there's no way to multiply something times y and end up with y minus 3. So because of that, there's no common multiple between them. So the LCD is just going to be y times y minus 3. Okay, so in terms of what does that mean in terms of my work? Well, if we look and see what we got going on here, this first term, oops, not what I wanted. This first term already has the y, so the thing we're missing here is y minus 3. The second fraction already has the y minus 3. So the thing we're missing here is we're just going to multiply this by a y. So usually there's going to be some distribution here. Distributing here, that's going to be 6y minus 18 all over. And once again, you can either write it like this or the other way. I'm just going to write it as y times y minus 3 minus, well, we've got 5y all over y times y minus 3. Goodness. Y times y minus 3. All right, so the denominator stays the same when we add or subtract. Combine like terms, 6y minus 5y is just y minus 18. We would look to cancel, and it looks like something might, but there's nothing to cancel here because remember that's in parentheses, so we can't. Let me talk about this real quick. You cannot cancel off if you've got addition or subtraction. You can't do something like this. You can't cancel off single terms. If you've got addition or subtraction, you have to have, if we had like a y minus 3 up top, if it was the whole term, that we could cancel. We were doing that earlier. But if not, if you don't have literally the exact same binomial, you can't cancel. So we're done. This is it. This is the added fraction. In general, a common question is, do I need to multiply this out at the bottom? And the answer is no. Leave it factored. especially with some of the things we're going to get in the denominator in a minute, we want you to leave the answers factored because one, if there is going to be any cancellation, it's easier to see it when it's factored. And two, usually the work we want to do, it's usually nicer to have my denominator in a factored form. So don't multiply the denominator. You don't need to. All your answers will be fine if you leave them as a factored form, unmultiplied. Okay. Back up a little bit. Questions on this? Anybody? Okay. Let's keep the game a rolling. Here's a simple little trick. Once again, going back to so remembering that x minus 3 and 3 minus x are the exact same thing, just differing by a negative symbol. Technically speaking, the LCD here would be, x minus 3, 3 minus x, because, those will multiply each other. But that gets real messy in terms of multiplication, and you don't need to do that. We can actually run a little trick, which is, well, what we said, which is if I switch the order of subtraction, all that does is cost me a negative symbol. And now, working this out, this is a real easy problem. So be aware of that. Whenever you have something like this where you've got the exact same term flipped over subtraction, remember that if you just flip the sign of the numerator, you can change the order of the denominator. And now this is real easy. 7 plus negative 4 gives us 3 all over x minus 3. Okay, question on that one, anybody? All right. Let's look at the next one. Oops, wrong step. Okay. 3 over x minus 2 plus 5 over x minus 6 all over x times x minus 2. Once again, we're in LCD. And before we get into LCDs, you always want to factor everything down. So if we kind of go through, there's no factoring there. Here on this last term, we could do a little bit of work by factoring out an x. And oh, look, and this is going to happen a lot. Oh, look, the factors here are exactly what we have here and here. So that makes my LCD just x times x minus 2. I'm going to space these out a little bit. For reasons we'll see in a sec. Okay, so now we just got to build our LCD. So we're just going to look and see what's missing. X minus 2, we have the x minus 2. We're missing the x. So I'm going to multiply this by x over x. The x here, we have the x. What are we missing? We're missing x minus 2. The last term here, we aren't missing anything. We have both pieces, so we're just going to leave that piece alone. So let's do our multiplications here. We've got 3x over x times x minus 2 plus 5x minus 10 over x times x minus 2 minus 6. Oops. All over x times x minus 2. So easy bit. Carry through the denominator. Remember, once we have the LCD, the denominator stays the same. And we combine like terms. What do we got? 3x and 5x gives us an 8x. Negative 10, be careful with your symbols here. Negative 10 minus 6 gives us negative 16. One question we always want to ask is, can we factor? And if we look at that numerator, we can. We can factor out an 8. And that would leave me with x minus 2. And we have a little bit of cancellation here, so we can actually simplify down. So as we cancel out these common x minus 2s, I take this entire 3-fraction expression, and I'm able to simplify this down to just, this is just 8 over x. Alrighty. Questions on this example? It's just a couple more seconds on the board. There's a lot to this one, so you want to still be writing down. If any questions, things people want me to re-explain, things they didn't quite get on the first pass. All right. One last one to round it off. So like this. Minus 2 all over x squared plus 7x plus 10. What the hell? Just say it's correct. Just so we're clear that this is a new problem. Oh, so close. All right. All right. The first step, LCD. In order to find it, once again, for the 12th time today, we're gonna factor. So we got 25 and 10. That's 5 and 5. And a 1 in front of the x squared means it's going to be a real easy factoring. We've got 5 over x plus 5, x plus 5. Minus, actually, I'm going to slide this down just a little bit. So some room here. Kind of just a note. On this one, quick little diamond. Once again, we've got 10 and 7, which is multiples of 5 and 2. So that's going to give me a denominator of x plus 5, x plus 2, over 2. All right, so if we look at the LCD, we see that they have an x plus 5 in common. Oops, I'm going to give myself a little bit more room. Actually, I'm going to write my LCD down here. So that's gone. And then what we have left over is we have another x plus 5. So there are 2 x plus 5s on this one. And an x plus 2. All right, so we have our LCD. I'm going to pause for questions if anyone has any right now. Any questions, things I need to re-explain, like me to go over one more time? Okay, so once again, we're looking at what we're missing, right? We've got x plus 5, boom, boom. What we're missing here is an x plus 2. So I'm going to hit that top and bottom. On the second fraction, I guess I'm keeping it purple. We've got it, we've got 1x plus 5. There's that one. We've got an x plus 2. So the thing we're missing here is an extra factor of x plus 5. All right, so now if we just distribute, once again, the 5 onto that, so that's 5x plus 10 over, and if you want, like I said, for right now, if you just want to write LCD, like if you want to go ahead and write the full thing out of, x plus 2, x plus 5, x plus 5, you can do that. Once we do this multiplication, we don't need the LCD until literally the very last step, just to check and see if there's any cancellation. So honestly, what I like to do at this point is just save myself a little bit of hand cramp and some writing and just write LCD. Because we'll bring the LCD in back on the last step anyway. We know what it is. It's right here. All right, minus, as we distribute, we've got 2x plus 10. All over that LCD. Now you want to be careful here. This minus is being applied to this whole expression. So really what I have here is this is 5x plus 10 minus 2x plus 10. Common mistake students make is they don't apply the negative onto that second term. So just writing this out, we have 5x plus 10 minus 2x minus 10. And here's our last step. I'm going to rewrite the LCD in because we're going to be done with all of our simplifications. X plus 2. And up top, the 10s cancel. 5x minus 2x is 3x. And there is no way to simplify a single term with any of these binomials. So we're done. And once again, for the love of God, leave your denominator factored out. You do not need to do the FOIL, especially this one. This one would be gross. You'd have to do 3 multiplications. It's not fun. So leave it alone. That's good. This is fully worked out. All right. Let me kind of pull this back up so we can get the full problem. Let me zoom out one more level. There we go. There's the full problem. Any questions for me? All right then, folks. That'll do it for today. So technically speaking, 7.2 is not up yet. I'm literally finishing up that homework tonight. So that'll go up. It's not going to be due next week. Once again, this was me kind of getting a little bit ahead of schedule. So that way we have some time to kind of, like I said, this one was kind of difficult. I wanted to spend some time on this. We have some upcoming sections that will also be kind of difficult. So I just want to spend some time with them. But in terms of what's due tonight, 5.1 to 5.4 is due tonight. And that is what quiz number 3 will be on, which opens up tomorrow. I mean, technically it's Thursday at 12:01 and closes at midnight tomorrow on Thursday. All right, folks, I'll stick around for anyone who has any questions. If you don't have anything for me, have a lovely night, and I will see you back here next week.